लैम्डा म्यू যেহেতু কোয়ান্টাম নাম্বার তার মানে আর এর ভ্যালুটা তো ডিসক্রিট করবে
হ্যাঁ ডিসক্রিট তো not continuous r এর value now these values which they can change with time. I will show you later on. So the thing is that right now, as we have already talked about, the density fluctuation excitations, they are in pretty high energy, they require high excitation energy. Low excitation energy in respect of vibrational excitations mean that we have shape vibrations, density remains fixed. So in case of, let us consider a drop of fluid, then this is the drop of fluid, right? Then if you consider there is a sort of excitation going on, this is a drop of fluid, okay, then how can I explain the vibration? For that, let me consider an equivalent sphere of radius r0. This is how it is done. Equivalent sphere of radius r0, and then I will be talking about fluctuation with respect to it. Okay, so if the equivalent sphere is larger, then the fluctuations would also be more, right? So I am writing the structure. Suppose there is a point at the surface. What is the value of r? This r will depend on, I am talking about the spherical coordinates, right? Because I am talking about departures from a spherical shape. So in this regard, cylindrical coordinates won't be useful, right? Neither will be rectangular coordinates, but spherical coordinates. So r theta phi. You see, so I have written down r theta phi, and this is the constant term. So this is the radius of the equivalent sphere, okay? And then certain excitations. So what are the excitations depending on r0, number 1, into the shape parameters. These shape parameters, alpha, lambda, mu, they will actually decide what the shape will be like. It will be like this motion or this motion or this motion, something like this. They will be the one to deciding. And then we have this Y structure as well. Now you can do the parameterization in a different way as well, but this is one of the most popularly accepted forms. Okay, now regarding the shape parameters, this lambda, you see, this alpha depends on lambda and mu. Now lambda is the order of mode of excitation, and there are a total of 2 lambda plus 1 possible excitations, corresponding to mu is equal to minus lambda to plus lambda. Now you must be wondering, sir, why are you making things so difficult? No, it is not that I am going to make things difficult. I am generalizing a topic, and when we generalize, we think about all possible things, and then maybe some of them will not be useful, then we will get rid of it. Let me show you an example. So let me first talk about lambda is equal to 1 case. Lambda is equal to 1 corresponds to the vibration of the center of mass. Now the simplest possible is just the center of mass vibrates. It will not bring any physics at all if just the center of mass vibrates, and that corresponds to t is equal to 0 isoscalar vibration. So it is just left apart. It doesn't give you any physics at all. Next is t is equal to 1 isovector vibration. That means the center of mass of neutrons and protons, they are vibrating, and that's the structure I told you previously, right? This one. So they are vibrating. So this corresponds to the t is equal to 1 isovector structure. Next is quadrupole vibration. What is quadrupole? Prolate to spherical, then oblate, then spherical, then again prolate, this structure. So prolate to spherical, then oblate, then again to prolate, spherical, then again to prolate, and so on. This is quadrupole structure. And next we can also have octupole vibrations as well. Okay, so here I have written down for small amplitude vibrations, I have written down the kinetic energy term and the potential energy term. Now, what do you see here in the kinetic energy term? Normally, what do you have? T is equal to half mv square, right? Now, here, this d lambda, it plays the role of a mass. This is identical to that of the mass. And the expression in the case for an irrotational flow is like this. So, you see, d lambda is proportional to rho into r0 to the power 5, or basically this is depending on the mass, so proportional to density. Also remember, lambda is also here. Okay, next, the kinetic energy term. Now you must remember there are two things. One is d lambda playing the role of mass, another is when I am talking about t is equal to half mv square, v means dx dt square. So what is the x over here? The entire shape fluctuation. Remember, we have got the two factors. One is alpha lambda mu, another is y0. Now y0 is just a constant. It is not that important. So the one which is actually the defining structure is alpha lambda mu. So that is the real x over here. Okay. So that's why we have done ddt of alpha lambda mu, velocity. Now what about the potential energy? Half k x square. So just x square, this is like that k, another constant. And this time, this is related to the surface and Coulomb energies of the Bethe-Weizsäcker mass formula. I am telling you related. Actually, it's a very pretty ugly expression. I am not writing it down, but you must understand what is the origin of this cylinder. Okay. Okay, next, what we are going to do is, so we will write down the total Hamiltonian H is equal to T plus V. Now, most basic approximation, all the modes, they are decoupled. One mode doesn't interfere with another mode. So lambda is equal to 1 doesn't interfere with lambda is equal to 2 or some other lambda. Okay, very basic approximation. Now if this is so, then not only H lambda but also this C lambda and D lambda, they will become constants of motion. So to start with, if this H is a constant of motion, then time derivative will be 0. So I have just written it down over here. And this will give me this expression from which I can identify that this alpha lambda mu, they are undergoing a small oscillations which with this frequency. Small oscillations with this frequency. What I am telling you is this, that I have told you the entire structure is vibrating, right? Now I have defined the structure as alpha lambda mu, and after considering the fact that the different modes are independent of each other, they are decoupled, they don't interfere with each other, then I am getting the frequency of vibration of each of the alpha lambda mu. Okay. And again, this is all for small oscillations. Important. Okay, so we have written down the Hamiltonian, then we talked about the constant of motion, and then we talked about the small oscillation frequency, right? Now, you can write down the Lagrangian as L is equal to T minus V, and then there is a process called quantization. It is a formal procedure after which we can talk about this entire excitation in terms of particle excitations. Entire process. Okay, this is a part of classical field theory, you can say. Okay, you will be learning in your next semester, I think, quantum field theory. But anyway, this concept is related to classical field theory, where we talk about fields. And any excitation in a field is a result of some excitation of particle, quantum particle. Anyway, you don't have to think about it in a lot. But just try to understand that then similar we can write down the Lagrangian, then do the quantization, and afterwards the entire excitation process I can simplify it and think of it in terms of particle excitation. And what is the particle in the case of vibrational excitation? That particle is the phonon. Okay, so this is the vibrational quantum of energy over here. Now this is quite similar, and this vibrational excitation you can think of phonon similar to how the sound wave propagate in a medium. Now each phonon is basically a boson. This is important. This is not a fermion anymore. This is a boson, and each phonon carries lambda h cross angular momentum with parity -1 to the power lambda. Okay. Now any even nucleus, you can think of it as zero phonon state. Zero means no excitation. Now slowly, in terms of vibrational spectrum, we will talk about higher phonon state excitations. And now I will show you the entire structure. Anyway, okay, so this is the result after quantization. I am writing down the Hamiltonian in this form, you see. Okay, the small oscillation omega lambda, and this is this Q alpha lambda bar dagger is basically the creation operator for lambda phonon. Creation, destruction operator. Hamiltonian, the stuff that you saw, the C and D, it can be after quantization, it can be written like this form. Okay. Now from here we can write down the eigenvalues like this. Okay, so this is written in the simplified form like this. Okay, now let me just consider very briefly what is the scenario when we have a single quadrupole phonon. Remember, only one. So one phonon, quadrupole vibration, lambda is equal to 2. So you can write it down from here, lambda is equal to 2. So this is the structure. So the ground state is 5 by 2, h cross omega 2. First excited state is E21. You can just see from here different values of it. So second excited state, third excited state, and so on. Now I will talk about the next part when we will consider two quadrupole phonons and see how the structure looks like. Okay, so finally the level structure, right? So as I was mentioning previously, while drawing the level structure, you must remember that each lambda phonon has an angular momentum J is equal to lambda. Okay. Now here I have shown the structure for quadrupole case. Lambda is equal to 2. Now quadrupole case, one phonon. This is the one phonon. What is the value of J? As I just told you, only one. So J is equal to 2 plus. Why plus? Parity minus to the power lambda is equal to 2. So plus. Next, n is equal to 2. Two phonons. Now, similar to the M scheme which we did previously in shell model, you can do the same stuff. You see, 2. M1 is equal to 2. Now, previously when they were fermions, we used to put different values of M, right? But now there is no restriction because they are bosons. So we can have identical M values as well. And using this, you can see you get the J is equal to 4. And similarly, if you change M1, you will get this value. And J, so now these are the positive projections. Similarly, you can take the negative ones. It will be a repetition sort of. So we have J is equal to 4, 0, 2 and 4. So this is the stuff 0, 2 and 4. Now this is for homework. You will do this at home and show it to me in your next class. That for n is equal to 3 phonon case, using the M scheme, we are getting J is equal to 0, 2, 0 plus, 2 plus, 3 plus, 4 plus and 6 plus. Now, interestingly, there are points missing, 1 plus and 3 plus. What do you think? Why are they missing? Because they correspond to antisymmetric states. And here we have got bosons, symmetric states. So these are the symmetric, and 1 plus and 3 plus are antisymmetric states. So they will be just not be, they will be eliminated here. Similarly here 1 plus 5 plus, they are antisymmetric states. So that's why they will not come in the structure over here. And this is the level scheme. You see n is equal to 0, 0 plus. Remember I told you all even ground state you can consider as a 0 phonon state. 0 phonon, 0 plus. Next 1 phonon state, 2 plus. Next 2 phonon states. Now when I am talking about 2 phonon state, you see what's the energy? 2 phonons, 2h cross omega 2. What's the possible value of J? 0, 2, 4. Now important, they are all degenerate. Okay. Next 3 phonon states. These are the possible values. Now they are all degenerate. But in experimental scenario, we observe that there is a small splitting between the three. Also there is a small splitting between each of them. They are actually not degenerate. Why? Because there is something extra to the Hamiltonian which we are missing. Okay, this is the result. You understand? This model is perfect if the Hamiltonian that we have chosen is the only one. But if there is something added to the Hamiltonian which is somewhat small, then the result will be the eigenvalues will somewhat change from this model. Understand basic perturbation theory? So here you in the experimental case you will observe small splitting. Here you will also observe small splitting. Okay, now let me ask you how to identify vibrational states. Actually there are two very basic tests for that. Okay, now in this part I have considered the first test. What is that? The first test is small n and large p, small number of neutrons and large protons, or small protons, small number of protons and large number of neutrons. Now when I am saying this, I mean of course the valency protons and valency neutrons outside the nearest magic number shell. Let us consider the case of 114 cadmium. So this is Z and N. So this means there are 28 valency particles or 2 valency holes. We will consider this number 2 in the valency proton orbit. Similarly, there are 16 valency neutrons. So see, the number is 2 and this is 16. One is smaller and another is bigger. Next case, 122T. Here also, proton 2, neutron 10. Okay. Now, what if the two numbers are more? Then you will observe rotational spectrum if both Vn and Vp are large. What is the reason? I'll tell you just for it. Now, this is the very first test. There is another very interesting, which is an experimental test of the model that we have done. Why have we done so many calculations if we are unable to verify with experiment? Isn't it so? So see, this is the second test. What's the energy of the 2 plus of n is equal to 2 state? 2, the n is equal to 2 plus of n is equal to 1. See, E22 by E21. You just see the calculations which we did in the last board work. It will be equal to 2h cross 2 divided by 1h cross 2 equal to 2. Now let's consider the case of 114 cadmium. If you see the experimental structure and you will identify the two energies corresponding to E22 being 1.208 MeV and E21 being 0.558 MeV, and so the ratio is approximately 2.16. So this way, these are the two very interesting tests using which you can identify which nuclei exhibit vibrational spectrum. Okay. Okay. Now, what's the reason for this n small value of valency neutrons and large valency proton, or small valency neutron or small valency proton, large valency neutron? What's the reason? You see for here, let us consider nucleus with a small Vp and Vn. Okay, see say Vn is equal to 2, Vp is equal to 4. So what's the number of Nn bonds? We have got only 2, so Nn bonds only 2. Now what is the value of Pp bonds? 6, Np bonds 8. Now you see, you must remember this important fact that Nn and Pp bonds, they have pairing interactions, and pairing interaction is very attractive in nature, unlike Np bonds which don't have pairing interaction. And so nucleus with large Nn plus Np compared to Np, very large values of Nn and Pp compared to Np, they will have very large binding energy. And here you will observe somewhat single particle behavior. Now let us go somewhat more where we have one value less, another value more. Say for example 114 cadmium. So here you see the binding energy is lesser. Why? Because Np is large. Because of this contribution of 32 non-pairing bonds. And as a result, the structure will be more prone to vibrations. Now what if both Nn and Pp becomes large? Then you will observe rotational spectrum. One very important point before I finish the lecture, you must realize that the energy required for vibrational excitation is always somewhat lesser compared to that of rotational excitations.